So, my name is Julien. I am the CEO of a company called Superheater, and I'm going to come back to this later. This is a presentation about streaming algorithms. Also, as a note, I tend to speak very, very fast, so please do not hesitate to calm me with signs, like slow down, I'll try. So, this is a presentation about streaming algorithms and JavaScript. As I told earlier, I am Julien51 on Twitter and other silos. And my website is superheater.com. Please, also, I want to take 1 minute for you guys to introduce yourself to each other. Maybe find someone close to you that you don't know, that you've never talked to. Because every time I sit, I usually don't know my neighbors. So you have 1 minute, please introduce yourself, exchange maybe your email or something, and then come back to the presentation. All right, ready? Ready? No? All right. All right, let's go. Hello?
We control the room!
Let's go! Okay, so some of you might know what that is. This is kind of a picture of the web, and I'm going to start with a little history of how the web is and how it is turning into now. So for the longest time, the web has been kind of a geography, right? A world where you move from a site to another site following links. You would have web addresses, which is a very geographical thing. Even the icons of our browser are very geographic. When you look at, obviously, Firefox, it's a map of the world with a fox on it. But if you look at Safari, it's a compass itself. So it's a very geographical approach of the web. And I think we're slowly turning into something that is more like this, where we have more and more of a time-based approach of the web, where it's just too big to just even think about how big it is. And the more and more the information comes to us directly. If you think at Twitter, I usually don't go very far in my timeline, maybe not even a day or something. Like I would go back maybe 10, 20 tweets, and the rest of the data just comes to me. And RSS reader has been the same forever. Facebook is the same, and more of the information that we consume online, these devices have notifications, and it's just data coming through us. So it's less and less about me browsing sites and more about me sitting and like getting vast amounts of data in my face. And this is actually happening at all stages of the web. More and more our website, which used to be basically some kind of application code and a database, which has a lot of states, is more and more of a system with a lot of queues and system where the data goes in, then move to the next step, and then to the next step, and then to the next step, and then is eventually served back to the user or even to another user. And at Superheater, we exactly deal with this. For those who are not familiar with what Superheater is, it's basically a distributed architecture to push RSS feeds in real time. So people will come to us, give us huge lists of feeds, and when I say people, it's mostly companies. They come to us and say, hey, I've got like 500,000 RSS feeds that I need to fetch. I just don't want to do it. Please push it to me. So we try to get this data, build this massive pipe of data, and push it to them in real time as soon as we can. And doing this has a lot of challenges that we need to solve. The first one is obviously memory constraint. If the pipe is huge, getting all this data in real time, and when I'm talking about all this data, it's a couple hundreds or thousands of updates per second. It has a huge memory impact, and you need to store it and forget it as soon as you can, because if you even store it for like a minute or so in memory, then everything explodes. The other consequence of this as well is like there is no like, well, I'm going to get all the data, and then when I'm done with it, then I'll start processing it. Like the data comes to you, and it never ends. It's actually even increasing in volume, so you start to have to do it right away. When it happens, you need to process it, and then fire and forget again. It's also real time. Like you cannot, again, wait for the data to be processed before you send it to the next step. Twitter cannot wait for the number of retweets or star on an item before they actually show you on the timeline. Like it arrives, they show it to you, and then maybe later they will show that there's been retweets and there've been stars or favorites on your content. This actually changes pretty much everything that we've known and used when building applications, including and starting with algorithms. Like you cannot use what we've used so far to build applications, algorithms that we've been using for years to build the next app. The easy solution that everybody, I'm sure, is starting to think about is like, well, why can't we do just windowing or sampling? Windowing would basically be like, fine, I'm going to keep the data for like a minute, do all my computation, then trash it, and then start again. So buffering for like 1 minute or a couple seconds. This works, even though it's very, it's also very inaccurate in a way that If you want to start growing the window, you will eventually come back to the memory problem that we've had. Sampling is maybe, rather than keeping all the data, is keeping maybe 1 every 10 or 1 every 100, and then you start seeing patterns from this. Same problem, you might be missing what the important data is, and you actually want to have a global vision and compute on the whole set. So we're not going to talk about windowing and sampling in this presentation. So let's start with max and mean. This is actually very easy. If you get a flow of data that comes to you, you want to know what is the max, what is the mean. The most common use case for this, is obviously finding kind of the best, the winner in a set of data that comes to you. That's really, really easy. You just keep a track of the maximum that you've seen. If the new data that you get is bigger than the previous one, then this is the new maximum, and then keep doing this. It's pretty simple. I'm going to build a little JavaScript code and so that you can see with a visualization how it's done. We have an object called streamMath, which is basically doing math better than hopefully regular JavaScript does. It gets data through the feed method, compares the maximum with the new value. The new value is greater, then keep it as the max. To test this and to show presentation, let's do a little thing that generates number randomly. So this is a function that generates a number randomly, and they're arbitrarily low. I mean, it's not a normal distribution. This new input thing just yields a number every 10 milliseconds between 0 and 1 using the distribution determined here. And we just output this so that we can put that into GNU plot. So let's do this. Just going to run this. If you see, that's basically what it does. And if I put that into GNU plot and then plot this, hopefully you will going to see this, which makes sense. Like the green line is the maximum, and all the points are the new points that are being added forever. Looks like I'm missing the end of the screen here, so you'll see here. What we can see here very easily is basically this algorithm as a little problem here. It knows too much. Basically, it keeps track of the old maximum, even though like maybe in a year, this old maximum is not really worth remembering. We need to make sure that the algorithm is smart enough to forget. And how do we do that without, again, keeping a window? It's actually pretty easy. We just use what we call amortized values. So doing this, rather than keeping track of, we keep track of the raw value, but rather than comparing the raw value, we add some kind of factor, which maybe is the time at which we've seen this value, or the index in the sequence. And by incrementing this, we know that all the values eventually are going to be smaller. For two values that are the same, the oldest one is going to be smaller than the new one, basically. And that actually works pretty well. I'm going to go back here. And if we go back to the visualization here, we see that quite quickly, obviously the highest one are kept in track, but if there's been nothing very high for a long time, then it's slowly the next higher value is kind of the new maximum. Does that make sense? So this is an easy way to compute maximum and have some kind of memory and like not just take the first highest value that we have forever being the top one. All right. It works pretty much the same with minimums. Rather than adding the value at which you see them, you remove the value at which you've seen them. Okay, next step is the average. This is a slightly more complex problem in the way that usually you compute averages by summing all the values that you've seen in the dataset, and then you count all these values and you divide the first by the second one. Problem that we have, obviously, we do not keep track of the values, so we have no way of summing them and counting them afterwards. Well, the easy way to do this is to keep running counts. So rather than just having the data and comparing to the previous one that we did before, now we keep track of both the sum and the count. Works pretty well as well, as we can see here. So as you can see, I'm pretty sure you maybe the function that we've used here is actually a random number between 0 and 100. And quickly, as we can see here, the average converges toward 50. That's the green line in the middle. Can everybody see it? Yeah. Quickly converges with around the middle of the curve. This is great, but the problem is sometimes your data set might have interesting properties. So like, like a different distribution, and the problem that we see with different distribution is, oh crap, is obviously that if you have a distribution that does basically a sinusoid, quickly the average becomes uninteresting because it just sits in the middle and doesn't really give you any insight on what data is. I've started this 10,000 milliseconds ago and it's already very close to 0. If I keep this running for like an hour, nobody will be able to see anything in the average. It would be meaningless. The value the solution to counter this is to kind of weight the averages, and rather than having the same weight for all the values in the past that the new data has, rather than having the same weight for all the data points that you've had, just use the previous average to compute the new average with the new number. So basically, you take the average at the t-1, multiply by weight, add the new value, and then divide by the weight plus 1. What this does is basically it just shrinks the importance of the older values into the current weight, the current average. And so we can do this here very easily. And we can see that in this context, basically the average still is obviously lower than the maximum and the minimum because it's an average, but at the same time it slowly starts to not decrease anymore, not change much based on what the input is. So this is obviously bending the math in a way that it's not the actual average over the whole data stream, but again, the whole data stream doesn't mean anything when you have this size of data. You need to be able to have a kind of a running average without the windows and keeping the data. Which is exactly what we do here. The next one is standard deviation. This really starts to be complex because, the main goal of standard deviation is to identify the outliers, the numbers that are either way above the average or way below the average. You compare basically how far they are from the standard deviation. The variance is the average of the distance to the average. This is kind of the math lesson that everybody learns. Basically, you compute the average, and then the variance is you compute the distance between all the points and the average, and you get what we call the variance. The problem with this is, as we've seen here, it uses the average. And if we change the average with every point we have, we need to recompute the distance for all of the points that we've seen in the past with the new average. Is that clear? So that's kind of a problem because obviously we don't keep the data and we don't really want to waste our time recomputing the average all the time. Well, that's great because some scientists, mathematicians, Koenig and Huygens, have actually found changed not changed, but like found that the equation has an equivalent that is much easier to use in our context, which is rather than computing the average, the distance to the average for all the values, you keep track of a running square, the sum of the running square, and you just subtract the square of the average. And then, so that's exactly what we're going to do here. We have rolling, we keep basically the new rolling number, which is the sum of squares, and for each new value that we get, we still increment the sum, still increment the count because we need it for the average. We also keep track of the sum of square, and then when we need the standard deviation, we just compute the square root of the sum of squares divided by the count minus the square of the average, and we can do that as well. And we'll see that this is the same distribution as before, a random number between 1 and 100, and the standard deviation stays around 30, I guess, yeah, a bit below this, which is expected, I guess, for this kind of distribution. That makes sense? Anyone has a question? Maybe not? Okay.
I don't understand that one. But you can move on.
All right. What do you don't understand?
I guess because we're looking for an average. I think there's just not enough data on it because each point should have a standard deviation, and you have. I don't get it. Never mind.
All right.
Sorry, it's my fault.
No, it's my fault. I should be able to tell you. But basically, like the regular, the point here is the regular standard deviation calculation cannot work because obviously we would need to keep track of all the data, right? So we transform that equation and use another one that allows us to do incremental calculation of the standard deviation. That make sense? Better? Awesome. Okay. Next one, medians and percentiles. This one is nearly, I mean, it is at this point not possible without keeping some kind of window or some kind of sampling, which is sad, but it also makes sense because the median is trying to find which value divides the set of data into two sets of the same size, one of greater elements and the other one of smaller elements. There's a way to do that with two heaps by keeping track of some elements, so it can still be pretty low in terms of memory. The algorithm is relatively simple. The first one is start with obviously two empty heaps and then get going. When you get a new number, if it's greater than the previously calculated median, add it to the heap of greater numbers. If you get a smaller one, then you add it to the other one. And then basically, if the length of either heap is greater than the other one, you rebalance. So you take one element from one and you put it in the other one. And the median is always the smallest value of the greater heap. That makes sense? So it's basically you always keep track of the middle here. The problem again, if you try to do this on a long time, you will keep the two heaps will obviously keep increasing, so you have a huge amount of memory that you need to keep. Luckily, you can still clean the data by removing data from the two heaps. The problem with this is that you need to make sure that you don't remove too much, because obviously if all of a sudden your time series or your series is slowly decreasing, you will slowly move all the data from one heap to the other one, and then you won't have enough data to keep track of what is the median here, which is a problem. All right. Another one that is interesting is in a huge data, if you've got a huge data set and of incoming data, and you want to keep track of the thing that you might have already seen, and make sure that either you've already seen because you don't want to look it up, or actually you want to make sure, in the context of, say, a distributed algorithm that would run across a huge data set, you want to identify unique profiles on say, social networks. You would have to keep track of all the profiles that you've seen, which can be too big. So a good way to do this would be to use Bloom filters. Basically, Bloom filters work in a way that they're very space-efficient probabilistic data structures that uses hash functions and dimensions to identify items that you might have already seen. So you set bits to 1 when you've seen some of the item using the hashes. The problem with Bloom filters is you can have false positive, which we'll see later, which means that they will tell you that you might have already seen some piece of data, even though you haven't seen it already. But you can never have false negative, which would be saying that you've seen something that you actually haven't. You haven't seen something that you actually have seen before. It's also very efficient, and increasing decreasing the probability of errors is kind of easy because you add a couple bits, and it's still very small to reduce significantly the amount of false positives that you may see on a data set. Here's a little example that I've stolen online, and it actually works pretty well. So basically, for each data that you see, you will add it to your vector. So these are the blue dots. Can you see the blue dots? Maybe they're too small, but basically for each word that you see, you add them. Ooh, what? Funny. Something's wrong. Okay, so basically you see like the yellow ones are the one that I've added previously. The blue ones are the one that I've just added. So every time I add a new word, I'm going to add Berlin here. It will just add new rectangles of the data that I've seen. And if I look for some data, it will tell me if it's there or not. So I've added Berlin, Paris is not there. If I look for Berlin, obviously, no, it doesn't work. Something's wrong here. Obviously, it's there. Sorry? Oh. Yes, good point. All right. And basically, Berlin now is in there. So Bloom filters are a great way to identify data. The problem that they have, though, is if you input a large enough chunk of data, you will end up increasing the amount of false positive by a lot. And you may eventually end up to a point where the Bloom filter will always say that you've seen you have already seen the data that you've inputted because it basically filled the whole data structure with once. I'm going to switch to the next slide. And you have different ways to deal with this. Either you can time limit these Bloom filters. So basically, you do a Bloom filter per hour, per minute, per year. And then you can do things like finding trending trends, basically. So if you do Bloom filters per minute, you fill it up. And then every time you get a data that matches it, you check if it was also in the last minute, in the previous hour. And you can see that a given term has been showing up pretty often in the past time very easily with this. You can also extend them by adding more bytes to the vector. The problem with this is like an infinite data stream. Obviously, the number of bytes is going to increase as well. So it doesn't increase as fast, but still, you may, with thousands and thousands and billions of items, you may end up having to keep extending, which eventually might be expensive in terms of memory. You can do what we call counting filters, which are basically filters to which you add and remove data. And you can either remove data by removing the data itself, or just decide that you decrement all the elements in the Bloom filter by one every amount of time. So every 5 minutes, every hour or so, you just decide that the Bloom filter is going to lose some of the data that it's seen before using this technique. And this is kind of the end here. This was really barely scratching the surface of how you need to handle these kind of problems of streams rather than considering huge data sets and state that you have. I would definitely recommend that you look into this. This is something that I've completely discovered a couple months ago, and this has been fascinating to me. This is now the end. I will happily take questions if you have any on this.